So, good morning, grade 12 students. In this session, we're going to continue with the nervous system of chapter 9, the function of the neurons. Document 1, we finish about the resting potential, and we talk about the resting potential. There exists a difference in the potential difference between the intracellular and the extracellular medium of the nerve fiber. It's polarized, meaning that it's negatively charged, and we identified that the resting potential is equal to minus 70 millivolt. It depends on the species, but here we're going to talk about this species, which is minus 70 millivolt. Also, we talk about the selectivity of the membrane between for the different ions like K plus and A plus that are transferred according to diffusion or according to the concentration gradient, active transport, passive transport. What is the source of energy? That is the ATP, phosphorylation of ADP into ATP, and we'll talk about this. Talk about the difference in the concentration of the ions in the intracellular and the extracellular medium in document D between two animals, between a marine animal, intracellular and extracellular, and in another animal, which is the mammal, intracellular and extracellular medium. Also, we talk about the Na plus K plus pump that is responsible for the transportation of the Na plus K plus ions. And this system is an active transport where we have to have the energy. This energy should be supplied in the form of ATP, adenosine triphosphate, and this is called Na plus K plus pump, or they call it Na plus K plus ATPase, since it needs energy in the form of ATP. And we talk about the concentration as well as some notes that you have to know them. Diffusion is the movement or the flow of a substance from a medium of high concentration or high amount or high value or high pressure or high volume to a medium containing low concentration, low amount or low volume or low pressure of this substance. We said about the active and the passive transport. Passive, it doesn't need energy. It takes place with the concentration gradient. Wherever the active, it takes place against the concentration. It needs energy, and the energy should be supplied in the form of ATP, adenosine triphosphate. And also we talk about the ADP that is phosphorylated. We add a phosphate group, so adenosine di means two, adenosine diphosphate, while upon phosphorylation becomes adenosine triphosphate, three phosphates. Dephosphorylation is the removal of a phosphate group, so ATP will convert into ADP. Also, we talk about the action potential, the different phases of the action potential. We talk about the resting potential, about the artifact or hypopolarization, depolarization. We talk about the repolarization and the hyperpolarization and the inversion of polarity. Also, we talk about the difference in the number of open channel like K plus and any plus channels during the different phases. And also we determined the nerve impulse and the action potential. We said that we have effective and ineffective stimulations. We said about the factors that affect the propagation of the nervous message that are the myelination of the nerve fiber, also the large diameter or small diameter, all of them, they affect the propagation of the nervous message, as well as we have the temperature. As the temperature increases, the the nervous message speed, the propagation of the nervous message will be accelerated and it will be faster than the normal. All of them, we discovered that. So now we're going to move to the document 4, sensory receptor and the nerve impulse. Already, we started with these topics or these ideas in the introduction. We talk about the different types of receptors according to their position or according to their type of energy or the stimulation. So let's start step by step. Document 4, sensory receptor and nerve impulse, on page 180 on your book. So here, experimentally, it's possible to stimulate each of the points of the neuron or of an isolated nerve to obtain a nerve impulse. But in vivo, the genesis of these impulses done by specialized neuron structures. What are these structures and how is the impulse triggered at the level of these structures? Let's start with the different types of receptors. Already we talk about these sensory receptors. They are nerve structures. They are specific to a given stimulus. According to the location, we have exteroreceptors and enteroreceptors. If you remember when we talk about extra, and enter. External receptors, these receptors, they receive information from the external medium, while enteral, they receive them about the internal medium inside or by the external receptor, for example, the sound, the light, for example, tasting and so on, into receptors. So we have external like the light, if you remember, photoreceptors, like the sound or the pressure, and somehow they are external sources. While enteroreceptors, they provide information about the internal medium. This is according to their location. While according to their type of energy of stimulation, we have different types. So according to their location, either they are external or entero. External, they receive information from the external medium. Entero, they provide information about the internal medium. About the type of energy. Yeah, let's start step by step. So here about the nature of stimuli. First, we have something called mechanoreceptors. Mechanoreceptors, they are the receptors that receive a stimulus like the touching, for example, hitting, slapping, touching, and we have pressure. For example, if you want to pinch your hand, your finger, these are called the stimulus is called pressure, and also we have the stretching. All of them, they are classified. The type of receptor is going to be a mechanoreceptor, and the sensory organ mainly is the skin, or the muscles, or it's maybe the vessels. So the first type is called the mechanoreceptor that receive stimulus like pressure, like touching, like stretching, and their sensory organs, they are the skin, the muscles, and the vessels. You're going to say, do you have to study these? You have to know them. You have to know which type of receptors. Thermo is related to thermal. Thermal, it's the temperature or the heat. So thermoreceptor, this is the second type of receptors. Thermoreceptors, the nature of stimulus is temperature variation, is the variation of the temperature. So if you have a high temperature, your skin is going to feel this. If you eat something very hot, your tongue will feel this. So these are according to differences in the temperature. So the organ they are the skin and the tongue. Skin and tongue, they respond to the temperature variation, which a type of receptor is called a thermoreceptor. Photoreceptor is the third type. Photoreceptor, it responds to the stimulus regarding the light. So this is the third type of receptor. It's called the thermoreceptor. It responds to the light stimulus, stimulation in the form of light, and mainly the sense organ is going to be the eye, since the eye is responsible for observing the light. And fourth receptor is called the nociceptors, and nociceptors. Nociceptors, number four, nociceptors. Nociceptors, they are for the stimulation that causes pain. Pain is stimulation, like for example, high pressure or high temperature, for example, going to hit someone or slap them or hitting them in a box, for example. This is a high pressure. So this will lead to a pain. Pain is going to be at the level of the nociceptors, while high temperature also is going to be at the nociceptors, mainly it's going to be the skin. While chemoreceptors, chemo from its name, chemo, this is the fifth type of receptors. Fifth types of receptors called the chemoreceptors. Chemoreceptors, they are transported molecules, the nature of stimulus, like for example, the tongue or the nose. For example, you taste something containing, for example, high concentration of salt, NaCl. So these are molecules, NaCl, salt. So this is regarding the tongue. Or you smell something bad or something nice or sweet, for example, using also some molecules. So these are the chemoreceptors. So till now, we have five different types of receptors. First one, mechanoreceptor, that responds to the touching stimulus, the pressure stimulus, or the stretching stimulus, mainly the skin, the muscles, and the vessels. Second type is called the thermoreceptor, from its name, thermoreceptor. It's related to the temperature. Third type is called the photoreceptor. It's related to the light. And fourth type is called the nociceptor for the pain. And the fifth type is called the chemoreceptor. It's related to the molecules, transporting molecules at the level of the tongue and the level of the nose. Yes, Padia, your question is?
Can the nociceptors can this count as a temperature variation or is a separate thing?
Nociceptors, mainly they are related to the pain. If this temperature causes pain, so it's classified as a nociceptor. The receptor is classified as a nociceptor. But if this high temperature, for example, a high temperature in Saudi Arabia, for example, you have a high temperature. Does it cause pain?
Sometimes
Cause pain?
you
If you
you
feel
feel the
hot,
heat. Yeah. You
you
feel
feel
the heat.
hot, you feel hot, but you feel pain?
Oh no no.
No, there is no feeling of pain. While, if, for example, if I bring something hot and I put it on your hand, this you're going to feel pain, and you're going to feel
Yes.
hot, both. So
Yes.
nociceptors and thermoreceptors at the same time. But if you feel
Okay.
only hot, this is only a thermoreceptor. Okay?
Okay.
Okay, great.
Yes.
This classification of these sensory receptors as mechano, thermo, photo, and we have nociceptors and the chemoreceptors. Moving to paragraph 2. Paragraph 2 talking about from sensory receptor to an action potential. The function of receptors is to convert the different forms of energy into electrochemical energy or action potential and transmit it to the nerve center. So the function of these receptors is to convert the different form of energy, like the heat, for example, like the sound, like the pressure, the pain, into electrochemical energy or to an action potential. Example about this, the Pacini corpuscles. Pacini corpuscles, they are touch receptors. They are touch receptors that are sensitive to the variation of the pressure. So they are sensitive to the variation of the pressure. If I told you, how can you classify the Pacini corpuscle according to which type of receptors that are found here? Who can tell me which type of receptors that are the Pacini corpuscle? They are touch receptors sensitive to variation of pressure. So which type of receptor? Yes, by raising your hands. Yes, Badia, what do you think?
Um, Mechanoreceptors.
Excellent. They are mechanoreceptors. Why? Because they are for touching. Touch receptors that are responsible for variation in pressure. So this is the key word here, the pressure. So if you see here, the pressure is what? It's for the mechanoreceptors. So they are classified as mechanoreceptor. Thank you, Badia. Let's continue now to Pacino corpuscle. They are touch receptors sensitive to variations of pressure. Each corpuscle consists of unmyelinated nerve, sensitive nerve endings surrounded by a capsule made of connective tissues. The nerve fiber joining this capsule is a myelinated one. So we have a myelinated fiber. So here we talk about the Pacini corpuscle. An isolated Pacini corpuscle. Please, all of you have to pay attention here because here we started the experiment and the explanation will start in this slide. An isolated Pacini corpuscle with its fiber, they are placed inside a physiological solution. Three electrodes, they are inserted in three different positions, okay, or different points on the nerve fiber, and an appropriate system allows the application on the capsule of a pressure of an intensity above the threshold. So it's called supranuminal intensity. Supranuminal intensity is above the threshold. Document B, which is this document, shows the recording obtained on the screen of the oscilloscope from three different points of the nerve fiber. So let's start step by step to explain this. First, we have the stimulus, which exerting the pressure here, was the one in violet. And then we have the receptor potential, the one in red. We have the generating and we have the action potential. Let's start step by step. First, without any stimulus, which is at point zero here, without any stimulus, the receptor potential and the generating potential and as well as the action potential, all of them, they are what? They are minus 70 millivolt, which means that there is no effective stimulus. There is no stimulus at all. So the resting potential will be at minus 70 millivolt. Why? When we increase the pressure, here they are exerting a pressure. This pressure, it will be in gram per centimeter cube. Okay, so when we increases to about 10 here, when we increases to about 10, the receptor potential increases to reach about 0 millivolt, if you want to say, and then it decreases as time increases from 0 to 2 milliseconds. So after 2 milliseconds, it increases to above the resting. It moves back to the resting at 0 minus 70 millivolts. Here it decreases after 2 milliseconds. Whereas the generating potential, we have an action potential, and with repeated signal, meaning that it has a repeat frequency. We have frequency here. So when we increase the pressure to about 10 gram per centimeter cube, here we have an action potential that reaches here, and it repeated itself. Okay, so we have here a stimulus, and we have the action potential was recorded. So here we can say that 10 gram per centimeter cube is related to as an effective one. And here we can deduce the following. So here, recording the action potential, all of them, they have the same, as you see here, all of them, they have the same what? The same amplitude. But the difference will be in what? We will see, according to the coding of the nervous message. So if I ask you, Hassan Watfa, what is the coding of the nervous message? The nervous message in the nerve fiber is coded by what? Let's see, Hassan. The nervous message is coded by what? Yes, Hassan? Hassan Watfa? Good morning. Do you hear me, Hassan? Okay, let's move to Muhammad. Yes, Muhammad, what do you think the coding of the nervous message?
It's called by frequency, not
And
amplitude.
not by the amplitude. This is an important characteristic. So here it's coded by frequency and not coded by the amplitude, since all of them, they have the same amplitude. So in the second phase, the pressures of increasing intensity, there's an increase the intensity of the stimulus and applied, and they are represented in document C. So we have different pressures. So here we have the pressure is about 0.5 here in this one, 0.5 gram per centimeter cube. And here it's about, let's say, 1.5 gram per centimeter cube. And in this one, it's about 2 to 2.5. It's between 2 and 2.5 gram per centimeter cube. So what happens? Here we have the potential difference in millivolt, and down we have the frequency of the action potential. The frequency, the repetition. So here is the relationship between the intensity, the receptor potential, and the action potential's frequency. So when the pressure was 0.5 grams per centimeter cube, here do we have an action potential? Pay attention here. The dotted line, it represents the threshold. Okay? Here the dotted line is present the threshold. Okay, so pay attention to this. So first one, yes, I want to start with yes, Ali Hariri. What do you think for the first one? For the 0.5, after applying a pressure of 0.5 gram per centimeter cube, I want you, Ali, to interpret the first one. And I'm going to interpret this, Ali. Only this section. Okay? And pay attention. This dotted line represents the threshold. Okay? Yeah, let's start. Interpret. So after applying a pressure of 0.5, and then you have to continue.
After applying a pressure of 0.5 gram per centimeter cube,
Yes.
what's
Potential difference.
PD? What is it?
Potential difference, PD, which is delta
Okay.
V. Delta V, potential
Okay.
difference. Okay?
The potential difference increased from minus 70 millivolt
To
to
about
around 60
minus
millivolt.
to
60
about
millivolt.
minus 60, minus 55. But it doesn't reach the
Threshold of
threshold,
excitation.
so there is no.
There's no action potential.
So this means that this indicates that what? This stimulus 0.5 gram per centimeter cube is what?
Ineffective.
Is an effective stimulus. Very good. Since it doesn't lead to the appearance of the action potential. Very good. Moving for the second one. Second one, let's move for Rama. Rama, what do you think for the second one? Can you explain the second one? Interpret. Rama works. I think she had a problem in connection. So let's move now to Rama. Can you hear me? Okay, let's move to Selena. Yalla Selena. The second one, 1.5 gram per centimeter cube.
After applying a pressure of 1.5 gram per centimeter cubed,
Hmm.
the receptor potential increases above the threshold of depolarization.
Okay. So we have an
This,
action potential
this leads to the increase in the action potential.
to the appearance of the action potential, but this action potential, it decreases with time. If you see here, it increases and then it decreases with time as time moves from 1 to 3 seconds. So it decreases with time. So this indicates that this one is effective or ineffective, Selena?
Effective.
Effective, since it leads to the appearance of the action potential, regardless of the decreasing in the level after about 3 seconds. So it decreases after 3 seconds, after 2 to 3 seconds, below the threshold of depolarization, but we have an action potential. But here the frequency decreases. So we have high frequency, and then it decreases with time. Moving for, thank you, Selena. Moving for Dana, 2.5 gram per centimeter cube. Yeah, interpret this, please. Yes, Dana? So I need new hands and new voices other than Hariri, other than Selena, other than Zayed. Hassan Watfa, yes.
After applying 2.5 of the pressure, the
Stimulus of
action potential
2.5. Wait a minute. First of all, 8 and then speak. First of
after
all,
applying 2.5
after applying a pressure of 2.5 gram per centimeter cube, then you have to continue, Hassan. These are not included in the exam. All these notes, they are not included. Yeah, start. Start.
after applying 2.5 gram after applying
pressure.
pressure 2.5 gram
شكلك عم
per
تاكل شيء مش
centimeter.
طيب، كرمال هيك عم بتغلط. يلا. Yeah, continue.
After applying pressure 2.5 gram per centimeter squared,
Pure.
the action potential increased from -70 till -30,
Okay.
which referring to the graph, it's shown that there are action potential.
Yes, and it stays above the threshold as time increases from 1 to 3. Then above the threshold of depolarization. So here we have increased frequency. Okay? But if you see here, all of them, Ya Hassan, they have the same one. All of them, they have the same amplitude. All the action potential, they have the same amplitude. But the only difference between them is what? Is the frequency. And here, you can explain the note that Muhammad said, that the coding of the nervous message in a nerve fiber is modulated, or it's coded by the frequency. And the frequency is the one that determines the effectiveness, or the, let's say, the strength of the nervous message or the stimulus. It's coded by frequency and not by the amplitude. All of them, they have the same amplitude. They differ only in the frequency, how many times it repeats itself. This is called the frequency. So here in this application, in this document C, it shows that the nervous message is modulated, or it's coded by frequency and not by amplitude. So here, number one, they said what type of receptor is the Pacino corpuscle that Badia said. Part two, they want us in probing the documents to compare the recordings obtained in document B, and then you have to state the characteristic of each potential recorder. Part three, they want us in a nerve fiber, the nerve message is modulated in frequency and not by amplitude. Already we described this. They said justify this statement. So here, if you remember, these are similar to the one that we solved it in the introduction, the application about effective and ineffective, and then we have the graph coding for frequency, higher frequency, or lower than the normal frequency. So Pacino corpuscle, they are mechanoreceptors, and they respond to stimulus from the external medium, the pressure. So they are classified also as exteroreceptors. So I classified the Pacino corpuscle according to their position and according to the stimulus. According to the stimulus, they are mechanoreceptor of pressure, and according to the stimulus, the position is exteroreceptor. Part two, they want us to compare the recording in document B, then state the characteristics. So before exerting a pressure on the Pacino corpuscle, the receptor potential, generating potential, and the potential recorded, all of them, they are minus 70 millivolts. After applying a pressure of 10 grams per centimeter square for 2 seconds on the Pacini, the receptor potential increases from 0 to about increases to 0 millivolt, and then it decreases back. At minus 70, it increases to 0, and then it decreases back slightly as the time moves, and it moves to the initial value after 2 seconds. While this time we have, let's say this one, from now on, you have to say it a train. Train meaning that a group of action potentials were recorded. It's called a train of action potential. Okay, so a train of action potential was recorded here. So a train of action potential was recorded in the generating area with frequency, it decreases with time, and also a train of APS, action potentials, is recorded with frequency. So this indicates that for a preliminary intensity above the threshold, the receptor potential is going to be local in a specific position, instantaneous, it occurs instantaneously, and it disappears with distance, whereas the generating area produces a depolarization followed by a potential. So you have to know from now on that the receptor potential is going to be local, instantaneous, and it disappears with distance. So this generating potential causes the appearance of action potential in the nerve fiber, and this action potential will propagate from where to where? From the receptor potential to generating one and to away from the side. So here it is moving and propagating. As we said, it propagates in a unidirectional manner. Dendrite, cell body, axon. Then dendrite, cell body, axon. Moving forward, part 3. Before applying pressure, we have the receptor potential. It's equal to minus 70 millivolt, and the receptor potential for sure, it's equal to minus 70 millivolt, which is the resting one. So after applying pressure of 0.5 gram per centimeter square, what happened? The receptor potential increases to about minus 70 millivolt, and then it decreases back to minus 70 in about 2 seconds, from 1 to 2 or 3. So it remains below the threshold. So there is no action potential in the nerve fiber. What does this indicate? هون أنا عملت explanation, عملت like interpretation for part 3. On part 3 they need nerve fiber justify a statement about the coding of the nervous message by frequency. So I made it like interpretation. So here, what does this indicate? This indicates that the pressure of 0.5 gram per centimeter square is an ineffective one. So I solve it in my own. And as that you heard the question is not interpret, but I didn't interpret like we solve it together. Okay, so this is ineffective. Why? Because it's below the threshold and it doesn't cause the appearance or the elaboration of an action potential in the nerve fiber. Why? After increasing the pressure to about 1.5 gram per centimeter square in about 2 seconds, the receptor potential, it increases above the threshold and reaches about minus 40, and then it decreases back to minus 70 in about 2 seconds, 2.5 seconds. This leads to appearance in the action potential with frequency, that this frequency, it decreases with time. So this indicates that P pressure equal 1.5 gram per centimeter square is effective and causes the appearance of the action potential above the threshold, and this will lead to the appearance of the action potential and the nerve fiber. So we have here effective stimulation. Okay, but after increasing the applied pressure to about 2.5 gram per centimeter square, what happened? The receptor potential increases to reach a value of about minus 30 millivolt, higher than the one obtained in the case of 1.5. So it increases to a higher level. So we have an action potential with a higher frequency than the one goes for 1.5. So here the frequency increases, but the amplitude of the action potential, it remains constant. It remains the same. This explains that this pressure 2.5 gram per centimeter square is classified as an effective stimulus. An increase in intensity of stimulation causes an increase in the frequency and not an increase in the amplitude. Since the amplitude, it remains the same during the whole process and the whole experiment. Upon increasing from 0.5, which is ineffective, or increasing to 1.5 to 2.5, so the amplitude, it remains the same, but the frequency, how many times it repeats itself, here it changes. So therefore, the nervous message and the nerve fiber is coded or it's modulated or it's affected by frequency of the action potential and not by the amplitude. So the nervous message is coded according to the frequency of the action potential, not according to the amplitude of this action potential. So all of them, they have the same amplitude, but they differ only about the frequency. Okay, so this is everything for our session today. Tomorrow we're going to continue with document 5, talking about the synapses, their structure, their function, what do they do, and sure, we're going to move into details about synapses.